Conservation of angular momentum is a very important physical principle, and the interesting thing about these physical principles is that we are studying this on our planet, or small planet in our galaxy, and then these principles actually govern the motion of even like large scale objects, on galactic scales also. So we've talked about again that we talked about torque as being defined as the rate of change of angular momentum, right? So conservation of momentum, let's quickly review that. So we said that if the net external force acting on an object is zero, then the momentum of the object of that system in particular is conserved, right? So similarly, if the net external torque acting on the object, on a system or an object is zero, then the angular momentum of that system is conserved. So again, you can write this as L equals constant, and also L initial equals L final. They all say the same thing. All of these three equations imply the same thing. Now, you might have seen ice skaters, right? When they rotate, they change they basically bring their hands closer, or they change the shape of their body, right, to change their angular speed. And so this is basically that principle that they use. So L initial equals L final, right? Implies that I initial omega initial is going to be equal to I final omega final, right? And so if you change your moment of inertia, right, you change your angular speed. And so this principle actually lets ice skaters change their angular speed by changing their moment of inertia. So again, if you look at it in this form, I omega has to stay constant for an isolated system. So if you increase I, then omega has to decrease, or if you decrease I, omega has to increase, because of this conservation principle that is embedded in nature. And so when planets, for example, change their sizes, planets or stars in particular, they undergo different phases. They also basically, if they're rotating, they would also follow this principle. And so this is a demonstration of this principle. This person, you can see, is holding two weights, and then when someone rotates him, he's essentially an isolated system. So when he brings the weights closer to his body, his angular speed increases. So when he brings the weights closer to his body, I omega again has to stay constant, right? So when he brings the weights closer, he's decreasing I, so omega has to increase. And similarly, this is also a very interesting demo, that you see that this person, he holds this wheel in this orientation. So and then when he changes the orientation, he gets an angular momentum. And so why does that happen? Let's look at this conceptually. Let's say that the initial momentum, right, is, I'm going to show this as a vector, right, is like in this direction. Right? So he holds the wheel. The wheel is, let's say counterclockwise, moving counterclockwise, and so the wheel's angular momentum is in the upward direction. So since these two objects are an isolated system, when the person changes the orientation of the angular momentum, he changes it to this, right? He flips the wheel, and then in order to conserve angular momentum, he gets a large angular momentum in the upward direction, right? So that these two add up to give you the initial. So these two vectors, right, should add up to give you this vector, so that the angular momentum stays constant. So L final has to be equal to L initial. And so this is something very non-intuitive from my perspective, and it's a very important physical principle. So let's look at this example of a solid sphere. The solid sphere has a radius r, right, rotating around its axis. So what happens is, due to some internal forces, like let's say a planet, so this happens, a star, this happens to stars, and their evolution. The sun, for example, after a few billion years, it's going to become a red giant, right? It's going to devour most of the planets around it. So when that happens, so due to some internal forces, the radius of the sphere increases to 2 times r. So what do you think is the final angular speed of the sphere? So again, use the conservation of angular momentum and think about the answer. We'll discuss it. So the answer is it decreases by 4 times. So you can see that so you don't really need the moment of inertia in this case because it's still a sphere, but just to you can write this down, and this, you don't really need this because this factor is going to be the same. It's still a sphere, right? Moment of inertia again is always some factor beta times mr squared, right? So the beta is less than or equal to 1. So if it's still a sphere, you don't have to worry about this beta. But anyways, we'll use this. So that again, you can exclude these 3 options, right? Conceptually, since the angular momentum is constant, it's an isolated system. When the sphere increases radius, right? Its radius increases, its moment of inertia increases, right? So omega has to decrease. So it has to be one of these 2 options, right? It's when you calculate it, it's the first one. So omega final, we need this, and now I final is equal to omega initial I initial, right? And so omega final is I initial divided by I final, and then times omega initial. So if you plug in the 2 by 5 mr squared, and then this is 2 by 5 m times 2r squared. Remember that the square is on both the 2 and r, right? And so omega initial. So this 2 by 5 cancels out, m cancels out, and you just left with 1 over 4 omega. So or omega initial, same thing. So this is why the answer is A. Okay, so let's look at this example, a conceptual question. So again, there's a beetle, right? The beetle is on a small disk, right, at the edge, right? Initially, the beetle is on the rim or the edge. So what happens is the beetle crawls towards the center of the disk, right? So what do you think would happen to these 3 quantities? Are they going to increase, decrease, or stay the same? What's going to happen to the rotational inertia? What's going to happen to the angular momentum? What's going to happen to the angular speed? Again, we're assuming that it's an isolated system. So pause the video and think about what is going to be the answer for these 3 parts. Again, so when the beetle moves towards the center of the rim, right? Obviously, r is decreasing. I is mr squared for the beetle. I'm just writing for the beetle. The total moment of inertia is the disk plus beetle, right? And so the beetle, nothing is happening to the disk, but the beetle is moving towards the center. So the moment, rotational inertia is going to decrease because of that, because r is decreasing, right? Now, angular momentum should stay the same because of conservation of angular momentum. It's an isolated system, so angular momentum stays the same. So, and omega, because of conservation of angular momentum, omega is going to increase, right? Because I is decreasing. The beetle is moving towards the center, I is decreasing, so omega has to increase to make sure that the angular momentum is constant.